So when n is a2, when n is equal to 2, you will get a2 into m plus 2 into m plus 1 plus m plus 2 p naught plus q naught, then a naught into mp2 plus q2 varum plus a1 into m plus 1 p1 plus q1 equal to 0. Similarly, continuing this way, when you take the coefficient of n, നമുക്ക് വരുന്ന general recurrence relation എന്ന് പറയുന്നത് an into m plus n into m plus n minus 1 m plus n p naught plus q naught plus a naught mpn plus qn അടുത്ത a1 term വരും. Continuing that way, last term will be an minus 1 m plus n minus 1 p1 plus q1 equal to 0. And so these are going to be our equations. ഇനി നമ്മൾ നോക്കിക്കഴിഞ്ഞാൽ, so the term in the first bracket, okay, that is repeating in a similar pattern. So that is first term will m into m minus 1 plus m p naught plus q naught varum. Second term വരുമ്പോൾ replace m by m plus 1. Third term will replace m by m plus 2, and in the nth term replace m by m plus n. So let us call it as f of m. So if you put f of m equal to m into m minus 1 plus m p naught plus q naught, അപ്പോൾ നമ്മുടെ equations എന്ന് പറയുന്നത് നമുക്ക് ഈ ഫോമിൽ വരും. a naught fm. Second equation you will have a1 into f of m plus 1 plus a naught m p1 plus q1, then a2 f of m plus 2 plus a naught m p2 plus q2 plus a1 m plus 1 p1 plus q1. Similarly, nth term എന്ന് പറയുന്നത് an f of m plus n plus a naught m pn plus qn. Continuing, you will get up to an minus 1 m plus n minus 1 p1 plus q1 equal to 0. ഇനി from the first equation, നമ്മൾ first പറഞ്ഞത് a naught cannot be 0. So since a naught is not equal to 0, you will get f of m equal to 0. First equation and you will get m into m minus 1 plus m p naught plus q naught equal to 0. So this is the initial equation, and this is a quadratic equation. So when you solve for the roots will be m1 and m2, and they are called as the exponentials of the differential equation at the regular singular point. Mean if m1 and m2n are distinct, so this is the initial equation. അപ്പോൾ നമുക്ക് second order x equal to 0 singular point ആയിട്ട് വരുന്ന second order equation വരുമ്പോൾ, so when you solve, look for a series of Frobenius series solution. So these are the recurrence relation you get. So when you solve for the recurrence relation, so first thing is you need to determine the value of m. So m is obtained by solving for this equation. ഇനി നമുക്ക് m കിട്ടിക്കഴിഞ്ഞാൽ നമുക്ക് പിന്നെ ചെയ്യേണ്ടത് a naught a1 a2 etc. അതിന്റെ values കണ്ടുപിടിക്കാം. ഇനി if m1 and m2 are distinct and do not differ by an integer, in that case we will get two linearly independent solutions. അപ്പോൾ നമുക്ക് Frobenius series solution ചെയ്യുമ്പോൾ you may get one solution or two solutions. So if m1 and m2 are distinct and if they do not differ by an integer, so if m1 minus m2 is not an integer, then in that case we will definitely have two linearly independent solutions. And again, if m1 and m2 differ by an integer, say if m1 minus m2 is equal to some j, the j is an integer, then നമ്മൾ recurrence relation ചെയ്യുമ്പോൾ when you do the write down the recurrence relation, what happens is the coefficient of aj in the j plus 1 recurrence relation will be 0. So you will get a solution corresponding to m1. ഇനി നമ്മൾ m2 ന് വേണ്ടി എടുക്കുമ്പോൾ, when you take the j plus 1 recurrence relation, the coefficient of aj is going to be 0. അപ്പോൾ നമുക്ക് aj യുടെ വാല്യൂ കണ്ടുപിടിക്കാൻ പറ്റില്ല. So therefore in In that case, we cannot solve for 8. And similarly, when you have the case where m1 equal to m2, m1 ഉം m2 ഉം രണ്ടും സെയിം ആണെങ്കിൽ ആ കേസിലും നമുക്ക് ഒരു m വാല്യൂ ഉള്ളൂ. ഒരു m വാല്യൂ വെച്ചിട്ട് നമുക്ക് you can find out only one Frobenius series in that case. So the case m1 equal to m2 can also generate only one solution. So these are the different cases where you will have two linearly independent solutions and one linearly independent solution. So we can conclude it as a theorem. So suppose that x not equal to 0 is a regular singular point for the differential equation. Y double dash is p of x y dash plus q of x y equal to 0. Assume that the power series for x into p of x and x square into q of x has radii of convergence are greater than 0. So suppose that the initial equation m into m minus 1 plus mp naught plus q naught has roots m1 and m2, and let us take m1 greater than or equal to m2. Then the differential equation has at least one solution of the form y1 equal to x raised to m1 summation n equal to 0 to infinity a n x power n on the interval minus r to r. So if you have an equation of this form, it will have at least one solution, and when m1 minus m2 is not 0 or positive integer, then the differential equation will have a second solution, which is of the form y2 equal to x raised to m2 into summation n equal to 0 to infinity dn x raised to n. And that is the eppozhum one solution undavum, at least one solution will be there. Second solution will be particularly occurring when m1 minus m2 is not 0 or a positive integer. So when it is 0 or positive integer, in that case you will have only a single solution of this form. So that is the theory behind the method of Frobenius. So that's how we obtain the general initial equation and the solution. And so in the next session we will look at a few problems based on this theory.